Welcome to Unit 6A Video Lesson 3. We don't have quite so much reading to go along with the video. Simulating motion with a grapher is our only topic, but I need you to actually have your graphing calculator and follow along. There are a lot of examples I want you to try and graphing on your own as you read that. The motion we are going to be simulating is projectile motion, and we're going to be simulating it using parametric equations. The x equation, or the horizontal equation, is v sub 0 cosine theta times t, and the vertical one is y equals negative 16t squared plus v sub 0 times sine theta times t plus h sub 0. Let's figure out what all of those letters represent, and then we'll talk about where we got those equations. V sub 0 is initial velocity. Initial because that sub 0 means at time equals 0. I'm always going to give you velocity in feet per second. T is time elapsed. Remember, that is also your parameter in the parametric equations, because that's your main variable. H sub 0 is initial height. It's going to be in feet. Theta is your direction angle, as usual, in standard representation. Now, where did we get these equations? Well, first let's talk about the cosine and sine. If we've got a little dude here, and he's throwing a ball or a javelin or whatever he's throwing at this vector, v, that speed of that vector has both a horizontal and a vertical component. If you'll remember from our vectors section, the vertical component of your vector is always going to be the magnitude of v times sine of theta, where this is theta. And the horizontal component is always the magnitude of v times cosine of theta. That's where these are coming from. This v sub 0, which is the magnitude of v, is multiplied by cosine theta to get the horizontal speed. V sub 0 times sine of theta was the vertical speed, or the vertical velocity. Both of those are in feet per second. H sub 0 is the height from which something is thrown. Like, this thing wouldn't have been thrown from h equals 0, it's however far off the ground this guy's hand was. That would be your h. Now, where did the negative 16 come from? That's gravity. The acceleration due to gravity is always going to be negative 16 feet per second squared as long as you're, on Earth. We're not going to be leaving Earth, so that's not going to change. So that's where these came from. Most of the time, that means that you can use these as usual, but sometimes it actually gets a little easier. What happens if an object is going straight up or down? We're not going to have that horizontal motion that we had when the guy was throwing the javelin or baseball or whatever we had. Now, it's going straight up and down. Let's say that this guy is just tossing a ball in the air. Whee! Here's the ball. That's your vector. You notice that we have a vertical component, so we still have our absolute value of v sine theta, but do we have a horizontal component? No, because our angle's 90 degrees. Please remember, sine of 90 degrees is 1. Cosine of 90 degrees is nada. It's 0. So what happens to these if this is replaced with 0 and this is replaced with 1? Our parametric equations just become x equals, well, technically 0. x equals 0t, we'll frequently use this just to be able to visualize it. And then our y equation turns into something that looks a whole lot more like what we saw in, say, Algebra 2, when we were just learning about quadratics. Now, we're going to start with an easy one where it's just going up and down, and then we'll move to an example that has both vertical and horizontal motion. A bottle rocket is shot straight up from a porch deck that is 10 feet off the ground at an initial velocity of 120 feet per second. We're supposed to set up the parametric equation to model the flight of the rocket. Well, x, our horizontal motion, isn't going to change. You'll notice in the reading from the book that they sometimes will say x equals t. That's if they want to really see the motion and it ends up making a parabola. Or sometimes they'll put they'll pick an arbitrary number, and let's say it's 5, and that will just show the vertical motion in a line, and you can trace to see how it's going up and down on that line. So sometimes we'll use one or the other, or both, and I'll show you that on your calculators. For the y equation, this is the one that most people have to really think about. We start with our acceleration component, negative 16 t squared. Then we add in our speed component, 120 feet per second. Because it went straight up, we know that we just have sine of 90, which is 1, so we are going to ignore that for now and just call it 120t. Initial height, h sub 0, is 10. This was h sub 0, this was v sub 0, and negative 16 never changes. Done! We've set up our parametric equation. Now how high will the rocket be after 2.5 seconds? For this, go to your grapher, turn it on, and make sure that you are in parametric mode. From here you need to go to y equals and enter your x1 and y1. So I'm going to use, say, x sub equals 9 as just a random place that isn't on the y-axis to show this motion. Let's say that it means that it's like 9 feet from your house or something, but it's really just an arbitrary number. Now I put in my negative 16t squared plus 120t plus 10 feet off the ground. Now let's set our window, because automatically it's going to be that whole like negative 10 to 10, negative 10 to 10. And our time is currently only going up to 6 seconds. That might be good, but we'll keep in mind that we may want to change that in case it takes more than 6 seconds for this bottle rocket to shoot up off the ground and then land. We don't want any negative x's, so I'm going to make this 0. And it's a bottle rocket, and I'm going to say 10 seconds works, sure. Bottle rocket, don't want any negative values, but it's probably going to shoot up pretty high, so I'm going to pick a pretty high number. If it's going 120 feet per second, let's say maybe 500 feet. See how it works. Graph. Well, that is just a line. But if we use the trace feature, we notice that it's going up as t goes up, and then it goes down. T is still going up, but notice that we're going down. So that is why, and notice that we didn't get all the way down because t stopped. That is why we're going to first look at this a little bit different. I'm going to have x equals t now, and then that exact same equation. So this equation, we'll notice when we graph it now, is a parabola. But why does it stop? Oh yeah. We only went for 6 seconds. Let's maybe go up to 10 seconds. See what happens then. That was our first set of equations. This is our second set of equations. And so we see that although the rocket was shot straight up into the air, if we make x equal t, we can kind of see the height over time. How high will the bottle rocket be after 2.5 seconds? Calculate value 2.5 seconds. When t is 2.5, x is 9, and y is 210. So, x equals 9, y equals 210. Which one of those tells you the height? Well, x is horizontal, and that's actually not anything right now, because remember the 9 was arbitrary. And y is 210. This is your answer. 210 feet in the air after 2.5 seconds. Now, that one you may have noticed you could have used just a simple quadratic equation, like from your Algebra 2 class. This one's slightly less simplistic. So let's begin. A baseball is hit from 2 feet above the ground, that's your h sub 0. With an initial speed of 95 feet per second, that's your v sub 0. At an angle of 63 degrees, that's going to be your theta. Set up the parametric equation to model the flight of the ball. We have to start with our horizontal equation. That's going to be initial velocity times, since it's horizontal, cosine of our theta, 63. That's our coefficient of t. And for our vertical equation, we have to start with gravity, negative 16 feet per second squared. That is the coefficient of t squared. Coefficient of t will be 95 sine of 63, sine of our angle. And then since we're not hitting this off the ground, we're hitting a baseball from 2 feet above the ground, we have to add 2. Parametric equation, check. Now, turn to your handy-dandy quackulator so that we can figure out the maximum height of the ball. We're going to start by checking that we are in the correct mode, degree mode, parametric mode. And once you are there, you can go to y equals and enter your two equations. 95 times the cosine of 63, end parentheses, times t. And for my y1, negative 16 t squared plus 95 sine of 63, end parentheses, t, plus 2. Before I graph this, I'm going to go to my window, because I have to think that this is going to be a little bit different than, say, what we were talking about in the last problem. It's a baseball going 95 feet per second, so I'm gonna pick 10 seconds for fun. Why not? And I'm going to pick negative 10 to 10. That doesn't make sense. So let's see, how far do we think this thing is going to go? We can't go backwards. 95 feet per second, let's say up to 200 feet. That might work. How high is it going to go? Well, it's not going to go below the ground, so no negative. And for y max, let's go for 200 again. See where we are left. Graph. And we've got a parabola. It appears that we almost had the window right, but we should probably make the x values a little bit higher. So let's make that 250. Graphing again. And we wait for it, wait for it. Ah, that seems to be working. Now the maximum height of the ball, we all know, is going to be right here. But what exactly is here? Well, when you were in algebra, you learned how to find the height of a ball using the vertex. Do you remember that? So we're going to go back here and be like, oh yeah, to find the vertex you needed to do negative b over 2a, and that would be your x-coordinate of the vertex, and then you had to plug it in to find the y-coordinate of the vertex. Well, I'm not going to make you do that, although I could easily make you say negative 95 sine of 63 all over 2 times negative 16 and figure out what that is, but I'm not going to make you do that, because if I make you do that, I'm going to have to make you do all the other algebraic things, and it gets kind of crazy. I'll show you how to do all of these algebraically at the very end of the video, but for now, we're going to use our handy-dandy quackulators. Now, in parametric mode, you don't have quite as many lovely calculator features when you go to second calc. That max and intersect and all of that are gone. All you have is value. And then you have this dy over dx, dy over dt. What? That's derivatives. You'll get to that in calculus. For now, we're just going to use the trace function. So not second calc, just trace. From here, we're going to trace all the way up until we get to the high point. It's kind of annoying, but it's the easiest way to do this without calculus. Alright, this seems to be the highest point. Let's see, 113.90. Can I get any higher than that? Nope, 0.56. And the other direction, oh, 0.91. Let's see if I can get any higher going that direction again. Went back down. So this is my highest point. That is going to be my y, because height is vertical. So the maximum height of the ball is 113.9. 113.9 feet. Now if we go back to our calculator, we see that 112 is how far it has gone horizontally at that point, and 2.6 is the time elapsed since hitting the ball at that highest point. Next, we've got how far will the ball travel, how long will it stay in the air. For both of these, we are focused on the end of the traveling. How far will the ball travel? Well, we're asking what is x when y equals 0. How long will it stay in the air? Well, when does it stop being in the air? That's when y is 0. But this time, instead of asking how far, far generally means horizontal. This time they're saying how long. That's time. So what is t? For both of these, once again, you can do it algebraically. I'll show you at the end of the video how to do it algebraically. But the easiest way to do this without calculus is to use the trace function, which I will admit is not the easiest function to use. Well, no, it's not hard. It's just tedious. So you have to wait, focus on your y, look for when it goes negative. Up, went negative, that's too far. So which one's closer, -7 or 1? That's definitely closer to 0. So I'm going to say at t equals 5.3, after 5.3 seconds, it has gone 228.5 feet and it's as close to 0 as the trace function is going to let us get. So how far did the ball travel? That's our x value, 228.5. I think it actually might have been 0.6 when we rounded. And how long did it stay in the air? Looking back at our calculator, right here, 5.3 seconds. We generally want to be about of 1/10 of a second accurate. So this was feet, and this is seconds. As long as your change of t is 0.1 or smaller, you're going to be accurate enough. It's not going to be as accurate as it could be, but you'll be accurate enough. 0.1 or smaller. You can change that in your window menu. You'll notice I made my t-step 0.1. If you make this t-step larger, your graph is going to get less smooth and it'll take less time to graph. If you make this t-step smaller, if you tried to make it like 0.01, it's going to take forever to graph, but it will be more accurate. I recommend t-step of 0.1 for most situations. Now let's talk about this last problem. 210 feet in front of where the ball is hit, there's a 30-foot high fence. Did the ball clear the fence? Now this one, we can still use trace, and we can check, and we can go backwards, and say, alright, 210 feet, so I'm looking for x to be 210. Oh, there was 211, 207. So around there, how high was that? 39, 32-ish. So, in between 39 and 32, we've crossed over a wall that was 30 feet high. Did it clear the fence? Yeah, that's higher than 30 feet. Yes, it was higher than 30 feet. At this point, if you really want to, you can stop watching the video. However, for those of you who want to remember, hey, I know we knew how to do this algebraically last year, please keep watching, because I'm going to talk about how we did these each algebraically.